momentum of a body is increased by 20%, then by how much percent its kinetic energy will increase. So to find this equation, first we have to determine the relationship between momentum and kinetic energy. We know that kinetic energy of a body is given by a half of its mass times velocity square, and the linear momentum of a body is given by mass times the velocity. So from this equation, directly a half of mv square, if I multiply by m over m, this means that I get 1 over 2 m square v square divided by m. Since m times v is momentum, so m square times v square is equals to the momentum square, so p square divided by 2m, or a half of p square over m is the kinetic energy. So the relationship between kinetic energy and the linear momentum of a body is kinetic energy is equals to the linear momentum square divided by twice of mass of the object. Then the question says that the momentum of the body is increased by 20%. Momentum is increased by 20%. Then by how much percent will its kinetic energy be increased? This means that if we have momentum P1, P2 is P1 plus 20% is P1. So this means 20% P1 means 0.2 of P1. This is equals to the final momentum is P1, 1 plus 20% is 0.2 simply. So the final momentum of the object is 1.2 times P1. So this is the P2. So P1 is initially P1 simply, but P2 is 1.2 times P1. So then the initial kinetic energy is kinetic energy 1 is equals to P1 squared divided by 2m, and the final kinetic energy is kinetic energy 2 is equals to P2 squared divided by 2m. This is equals to, since P2 is 1.2 times P1, which is 1.2 P1 the whole square divided by 2m. So this gives me that 1.2 square is 1.44 P1 square divided by 2m. So this is the values of the final kinetic energy. So the percentage increment of kinetic energy is given as, this is the kinetic energy final, or kinetic energy 2 minus kinetic energy 1 divided by kinetic energy 1 times 100%. So this is the increment of the kinetic energy. So to find this, if we substitute the value directly, kinetic energy 2 is 1.44 P1 squared divided by 2m minus kinetic energy 1 is P1 squared divided by 2m into 100% times, and divided by kinetic energy 1 is P1 squared divided by 2. So this gives us directly, we can take P1 over 2m from all this equation, P1 square over 2m into 1.44 minus 1 divided by P1 over 2m times 100%. So P1 square is cancelled by P1 square, 2m is cancelled with 2m, and we have left only with 1.44 minus 1, which is equals to 0.44 times 100%. So 0.44 times 100% means simply we have 44% increment. So the kinetic energy of the object is increased by 44%. The correct answer is on alternative D. when we move on a sandy ground, if this is a sandy ground, so it is so difficult to move on a sandy ground because our feet is stuck into the sandys. This means that the action force which the feet applies on the sandy ground is greater than the reaction force which the sand acts on our feet. This means that it is difficult to walk on a sandy ground. Therefore, the correct alternative which explains this phenomena is on alternative C, which says the action of the feet on the sandy ground is greater than the reaction of the sandys on the feet. A car of mass 1500 kg is moving with a velocity of 30 meters per second. So then it applied the brakes, and the friction between the tire and the road make it to skids, and finally the car come to rest here. The final velocity of the car is 0 here. How far it has traveled before coming to rest? So the equation required the displacement is of this car. So this equation is the combination of kinematics and dynamics. So we use the kinematic equation and also we use the dynamic equation to find the solution of this equation. The dynamic concept helps us to find the acceleration of the object. Since the velocity of the car is reducing with time, its velocity is decreasing, and finally the car stops and come to rest. So this means that there is a force which is opposing the motion of this object. So the force which causing the deceleration is the frictional force F. So the frictional force is causing an acceleration. F is mass times acceleration. But the frictional force is in the opposite direction of the motion, so I can make it negative here. So from this equation we can get the acceleration of the object is minus F frictional force divided by the mass of the object is. Then the acceleration of this object is minus 600 Newton divided by 1500 kilogram, which is directly equal to this 0 cancel and this 0 cancels. This base 3 is 2 and this base 3 is 5, so minus 2 over 5 meter per second square or Newton per kilogram. Since the car is slowing down, the acceleration is negative. That means it is decelerating. So since we know the acceleration of the object, which is minus 2 over 5 meter per second square, and the initial velocity of the car is 30 meters per second and the final velocity is 0, then how far the car has traveled before it come to rest. So we have A, U, V and S, so we don't consider T here in this equation. So I use the Suvat equation which do not include the T. That is the fifth equation, which says V square minus U square is equals to 2as always. Since the final velocity is 0, so minus U square is equals to 2 times acceleration times the distance traveled. So the distance traveled is minus initial velocity square divided by the acceleration. So if I substitute the value I have, then this is minus 30 meters per second, the whole square divided by 2 times acceleration is minus 2 over 5 meters per second square. So then finally we have S is equals to minus 900 meters square per second square divided by minus 4 over 5 meters per second square. So these minus cancel each other. The second square cancel. 1 meter is cancelled by 1 meter and only 1 meter is here. So if I divide this number, it is something like 5 times 900 meter divided by 4, which is directly equal to 1125 meters. So this means that 1.125 kilometers. So the correct answer is on alternative C. block is placed on an inclined plane, which is inclined at some angle theta. Then this angle is raised, that means the inclined plane is raised and theta is increased, but still, due to the friction between the surface and the block do not slide. So what is the maximum possible values of theta? That the block will remain at rest. That is when the block is in its limiting equilibrium. That means it is about to slide. So we have to apply here the concept of dynamics. If the block sits like this, the first thing is the free body diagram. We draw the weight of the object always down vertically to the center of the earth, and the normal force is always act perpendicular to the plane. This is normal force Fn, and the frictional force which opposes the motion of the block, that means which prevent the block from sliding down, is acting upward. And we can resolve the weight of these objects. One component is acting down the plane, that is mg times sine of theta, and the other component is which is opposing the normal force, that is mg cos theta, since this theta and this theta are equal. So this is the free body diagram for the block. Then since the block is at rest, all these forces are added together and must give us 0. So since the normal force is acting up, normal force minus mg cos theta is equal to 0. Then from this equation we can say Fn is mg cos theta. This is the equation you already know. And the second equation is from the components of the forces along the inclined plane. So the frictional force minus mg sine theta is also 0. Then from this equation we can write that the frictional force is mg times sine of theta. This is equation 2. Then we know that from the definition of frictional force, which says frictional force is always the product is of the coefficient of friction times the normal force, which is equals to mu times Fn is, we have already calculated, that is mg cos of theta. So this is the definition of the frictional force. Then if I equate this equation with the equation 2, which says F is equals to mg sine theta, since F is mu mg cos theta, so mu mg cos theta is equals to mg sine of theta. So I can cancel mg from both sides. Mu cos theta is equals to sine of theta. Then I divide both sides with a cos theta. Then mu is equals to sine theta divided by the cos of theta, which is tan of theta. Since mu is given, it is 0.3. So the theta angle is theta is equals to the tan inverse of mu, or the coefficient of friction, which is equals to the tan inverse of 0.3. So the answer is on alternative B. So two cars collide each other and move together, or they are entangled together. The car of mass m1, which is initially at rest, and car 2, which is 2000 kg, initially moving with 100 km per hour, collide car 1, and the both car move together as one parties, or they are entangled. So what is the final velocity of the combined system? So we can do this equation from the conservation of the linear momentum, which says that the conservation of linear momentum of two systems is given by m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. So initially car 1 is at rest, so u1 is immediately 0, and after collision the cars are entangled and move together, so v1 is equals to final velocity of 2, or simply we can say v. So then we can write the equation like, and m2 times u2 is equals to m1 plus m2 times the final velocity v. Since v1 and v2 are equal, we can take common as a v. So then the combined velocity of the system is given by m2 u2 divided by m1 plus m2. So if we substitute the values of m2 is directly equal to 2000 kilogram times the initial velocity of car 2 is 100 kilometer per hour. 100 kilometer per hour. It is divided by 2000 plus 2500 is 4500 kilogram. So the sum of the two masses are 4500 kilogram, that is 4500. Then the kilogram cancel with the kilogram, this 20 cancel with this 20, and finally we have 2000 kilometer per hour divided by 45. But the equation required the answer with meter per second. We have to convert this kilometer per hour into meter per second. That means we multiply it by 1 divided by 3.6. So the final answer is, if we do this simply, 2000 divided by 45 times 3.6, which is equals to 12.34 meter per second. So the final answer is on alternative D. A wooden block is loaded with a book and it's sitting on a concrete floor which is rough. That means this surface has a friction. It is imparted with the force F and get the velocity of 8 meters per second. So then the friction acts to slow down the velocity of this object or this block, and finally the block come to rest after it has traveled some distances. So what is this distances, or how far it can travel before it come to rest? So then the velocity of this block reduces time and it finally zero here, or when it is stopped. So in this case, the frictional force is making the velocity of the object is to reduce. That means to make the block to decelerate with some values of an acceleration. So then we know that from the free body diagram of this block, then the weight of the object or the block is mg downward, and the normal force Fn is exactly upward, and the frictional force is acting into the opposite direction of the motion. So we know that since the acceleration is along this direction, that means along the plane, so normal force minus the mg gives us 0. That means the normal force is mass times gravity, and the frictional force, which is retarding the objects from accelerating, which is given by equal to the coefficient of friction times the normal force. So then if I substitute this value, the frictional force is mu times mass times gravity. So this equation is from the diagram given. The object is reducing its velocity with time. So the force which making the object is to stop or reduce its velocity is the frictional force, which says that minus of the frictional force is mass times acceleration. That means the frictional force is making the object to decelerate. So if I substitute the place of friction with mu mg, negative of mu m times g is equals to mass times acceleration. So m cancel from both sides. So acceleration of the object is minus mu times g. And then when the object comes to rest, so we have an acceleration a, which is minus mu times g, and we have the initial velocity, which is 8 meters per second, and we have the final velocity, which is 0. Then what is the displacement of the object is, and if the coefficient of friction is 0.8. So we can do this by using the fifth equation, which do not include the t. So which says v square minus u square is equals to twice of as. Then final velocity is immediately 0, and the distance traveled by the object before it come to rest is minus initial velocity squared divided by 2a, or which is equals to minus mu squared divided by negative 2 of mu times g, because since acceleration is negative of mu g, so this negative cancel from both sides, and we have left with the displacement is the initial velocity is 8 meters per second, the whole square divided by 2 times 0.8 times 10 meters per second square. So 8 square is 64 meters square per second square, and this number become 16 meters per second square. So second square cancel second square, and 1 meter cancel 1 meter, and we have only with a meter. So 64 divided by 16 is only 4. So the block traveled 4 meters before it come to rest. So the correct answer is on alternative C. Kilogram body and move this through the displacement S, where the displacement of the object is given as a position function. Then after 4 seconds, what is the work done by the forces F? So we know that work done by force is given by the dot product is of F and S if force and displacement are parallel with each other, magnitude of F times the magnitude of S. So then from this equation, just we see that force is calculated according to the Newton's second laws of motion, which is mass times acceleration, but acceleration is always given as the second derivative of position function with respect to time. So this means that the acceleration of the object is directly given by d by dt of d by dt into 3t minus 4t square. So if we first derivate, the derivative of 3t is 3, and the derivative of minus 4t square is minus 8t. d by dt of 3 minus this derivative is 8t. If we derivate the second time again, the acceleration become minus 8 meters per second square. So this is the acceleration of the object. Then the total force acting on the object is equal to the total force is mass times acceleration, which is 3 kilogram times minus 8 meters per second square. So if we multiply this number together, we have minus 24 Newton. So this is the total force acting on the object. And the displacement traveled is the displacement traveled by the object is the x2 minus x1, or the vector differences of the position function. So x2 means x where t is equals to 4, or the final position of the object is. So x2 is the x of t is equal to 4 seconds, which is equals to 3 times 4 minus 4 into 4 square. So this is equals to directly minus 52 meter. This is x2, and x1 is the position of the object is at x of where t is equal to 0. This is immediately 0. So the displacement, which is the difference in position function of the object, that is minus 52 meter minus 0, which is minus 52 meter. So we have the both displacement and the force acting on the objects. So the work done by the force is equals to the force minus 24 Newton times minus 52 meter. So if we multiply this number together, we have 1248 Newton meter is given as joule. So the correct answer is on alternative C. Two masses M1 2 kg and M2 3 kg are connected with a light string and pass over a frictionless pulley. Then what is the acceleration and tension in the string in terms of G, or in terms of the gravitational acceleration? So we know that in free body diagram for mass M1, G is downward and the tension in the string is upward. Therefore, this mass is moving up because M1 is less than M2. That means M1 is moving up and M2 is moving down this way. So just we can say that tension minus M1G is equals to M1 times acceleration. This is equation 1. And from the free body diagram of mass 2, just we can see that M2 is moving down. This is M2, it's moving down, M2 times G, and the tension is tension T, and the string is upward. So in this case, we can say that since M2 is downward, M2 G minus T is equals to M2 times acceleration, which is equation number 2. So from these two equations, we can solve for acceleration and the tension in the string. So from these two equations, just we can say the first equation is T minus M1G is equals to M1 times acceleration, and M2G minus T is equals to M2 times acceleration. Then if I add these two equations, T minus M1G plus M2G minus T is equals to M1 plus M2 times A. This means that the acceleration for the both objects are the same because two masses are connected together by the string. So then T minus T cancel each other and we have left with G as a common end, M2 minus M1, which is equals to M1 plus M2 times A. So then the acceleration of the object is A is equals to directly into M2 minus M1 divided by M1 plus M2 times G. So M2 is 3 kg and M1 is 2 kg. So 3 minus 2 is 1. We have left with G here, and M1 plus M2 is 2 kg plus 3 kg, which is 5. To find tension, take one of the equation. For example, equation 1, T minus M1G is equals to M1 times acceleration, and we have an acceleration which is equal to G over 5. Then we can solve for T. So then from this equation, T is equals to, if I transfer M1G to this side, directly I can get M1 as a common end, A plus G, which is directly equal to M1 into G over 5 plus G, which gives me directly M1 is 2 kg, 2 into G over 5 plus G. This is equal to 2 into 6 G over 5, which is equals to 12 G over 5. So the tension in the string is 12 G over 5 and the acceleration is G over 5. So the correct answer is on alternative A. two masses A and B are connected with a light string and passed over a frictionless pulley. Mass B is hanging down the table and mass A is just sliding over the table. The question says that what is mass C that must be placed on A to keep the mass A sliding over the surface of the table if the coefficient of friction is 0.2 and mass A is 10 kg and mass B is 5 kg. Then what is the values of mass C which prevents mass A sliding over these surfaces? So directly we can apply here the dynamics. When we take mass B, if this is mass B, it's hanging by a rope, then there is a rope or the string with a tension, and mass B times gravity is downward. This is the free body diagram for mass B. So this is directly gives us that mass B times gravity minus tension is equal to 0. We make equal to 0 because the sum of all the force acting over all the system is 0, because just we are assuming that if C is placed on A, the system is not moving. That means mass A is not sliding over these rough surfaces or rough table. So then from this equation, I say this is equation 1, and if I draw the free body diagram for mass A and C, if this is the surface of the table, this is mass A and mass C is sitting over it, and this is the tension. There is a frictional force which opposes the tension forces, and the weight of the objects are acting downward. This is mass A plus mass of C times gravity. Mass A plus mass C times gravity is downward, and this one is the normal force Fn. So we know that the tension T minus the frictional force is equal to 0 since the system is at rest. So we can say that T minus F is equal to 0, means T minus, since the frictional force is mu times Fn, so this is equal to 0. So from this equation, if I substitute the values of the normal force, tension is equal to directly mu times Fn, which is equal to mu G into mass A plus mass C. So I take this as a second equation, and from equation 1 we know that equation 1 says that equation 1 says that MB G minus T is equal to 0. Then T from this equation can be T is equal to MB times G. Then if I substitute the values of T in this equation, so directly I can get that MBG is equal to mu G into MA plus MC. So G cancel from both sides, and M of B is equal to mu mass A plus mu mass C. Then if I determine MC from this equation, directly it says that MC is equal to MB minus mu MA divided by mu. So MC is equal to MB minus mu MA divided by mu. So this is directly MB divided by mu minus MA. So if I substitute the values, MC is equal to, since MB is 5 kg divided by mu is 0.2 minus 10 kg. So this value become 25 kg minus 10 kg, which is directly equal to 15 kg. So the correct answer among the given alternative is A, which says 15 kilogram. So the values of mass C is 15 kilogram, which prevents MA from sliding over the surface. The mass A is at the height h naught above the ground. It has a potential energy directly mgh naught. Then this system, which has mass B, which has 3 times m, has no potential energy here, so it is at the lowest point. It is at its lowest point. So if A is released and collide with B and move together and rises both systems at some height h, which is less than the initial height h naught at which A is initially raised. So in this case, all the potential energy of the system A is transferred to B and move together and raise the both systems to the height h's. So the height above which they raised is calculated as, so the mgh naught of mass A is directly equals to m plus 3 times m of g times h they raised. That means the potential energy at this point is equals to the potential energy at this point, which is the potential energy at the point C, or at this point. So from the conservation of energy, the potential energy at this point is equals to the potential energy of the combined system at these points. So just we can say that mgh naught is equals to m plus 3m is 4 times m g times h directly. So we can cancel m from both sides and g from both sides. Then the height above which the both system can raise is the initial height h naught divided by 4, h naught over 4. So the correct answer is C.